In this lesson, we'll do a few examples using the fundamental theorem part 2. So first, let's remind ourselves what the theorem actually tells us. So it says that to compute the definite integral, a to b f of x dx, we first need to find an antiderivative capital F, and then plug in our upper limit b, our lower limit a, and subtract the two numbers. So calculate capital F of b minus capital F of a. So in our first example, we have integral 0 to 2 of x squared dx. So our inside function, what we call our integrand, is our little f of x equals x squared. So the first thing we need to do is find an antiderivative of this function. So we know that to get our antiderivative, we're going to add 1 to our exponent. So we get x to the third power. And then we're going to put a 1 over 3 in front so that when we pull down the 3, we're just left with x squared. And in general, when we do antiderivatives, we get a plus c. We'll see in a few moments that when we do definite integrals, we can actually leave out the plus c, but for now we'll put it in and then talk about why we don't have to worry about it. So our fundamental theorem tells us that this is going to be equal to capital F of 2 minus capital F of 0. So let's go ahead and compute what that's going to be. So when we plug in x equals 2 to capital F, we're going to get 1 over 3 times 2 to the third power, this is a 3 here, plus c, and then minus 1 over 3 times, now we're plugging in our lower limit x equals 0, so 0 to the third power plus c. And so what you see here is that anytime you do one of these, you're always going to have a plus c and a minus c. So when you're doing definite integrals, so when we have our numbers as upper and lower bounds, when we're doing definite integrals, you can actually just leave off the plus c because it's always going to cancel when you plug in your bounds. So this then is going to become 2 cubed, that's 8. So we get 8 over 3. This 3 keeps having trouble showing up. So we get 8 over 3. 0 cubed is 0, so we just get 8 over 3 minus 0. And so our final answer here is just 8 over 3. So the integral from 0 to 2 of x squared dx is equal to 8 over 3 as our final answer. So let's common notation so that you don't have to write out your capital F every time. So typically you'll see this written as integral 0 to 2. So we had our x squared dx. So you'll see this written in the following way. So we'll find our antiderivative, which we knew is 1/3 x cubed. And again, normally we have a plus c, but we know it's going to cancel, so we'll just leave it out. So we get 1 over 3 x to the 3. And then instead of writing capital F of 2 minus capital F of 0, the shorthand notation is you put a bar from 0 to 2. And what that means is plug in your upper limit, which is 2, and then plug in your lower limit, which is 0, and subtract. So again, this is just shorthand notation for what we did here. So this then is going to give us, when we plug in 2 cubed is 8, so we get 8 over 3 minus 0 cubed is 0, so we get 8 over 3 minus 0, or 8 over 3, which is of course what we got previously. So the point of this at the end was just to illustrate this notation, which saves you a little bit of writing when you're doing these problems. So now let's look at what this tells us graphically. So this says that if I graph the function y equals x squared, then the area between the graph of this function and the x-axis from 0 to 2 is equal to 8 over 3. So this area is equal to 8 over 3. And you remember from the example that we did in class, when we did this using a Riemann sum, so a limit of finite sums, we also got 8 over 3. So we get the same result using our fundamental theorem part 2 and our limit of Riemann sums. Of course, the fundamental theorem is much easier to implement because it says we just need to find our antiderivative and then calculate this number f of b minus f of a. But it is useful to verify that we got the same area using our limit of finite sums as well as the fundamental theorem. Let's do one more example. Here I have the integral from 1 to 4, 2 root x plus 3x squared minus 1. So we know the first thing we need to do is get an antiderivative of this inside function. So to make the antiderivative process easier, the first thing I'm going to do is go ahead and rewrite 2 root x as 2x to the 1/2 so that I can easily find my antiderivative. So this is going to give me, to get the antiderivative of x to the 1/2, I'll add 1 to my exponent and get 3/2, and then I need a 1 over 3/2 in front to cancel. Antiderivative of 3x squared is x cubed, and antiderivative of 1 is x, and then again I'll use this notation that just tells me plug in 4, plug in 1, and subtract. So our antiderivative here was 2 times 1 over 3/2 x to the 3/2 plus x cubed minus x. So this entire expression is our capital F. And then what this notation here is telling us is compute the number f of 4 minus f of 1. So now we'll just simplify and then we'll plug in. I have a double equal sign here. So 2 over 3/2, the 3/2 flips and we end up with 2 times 2 over 3. So that gives us 4/3 x to the 3/2 x cubed minus x, which gives us, I'll plug in x is 4. So we get 4/3, 4 to the 3/2 plus 4 cubed minus 4. And then subtract off plugging in 1. 4/3, 1 to the 3/2 plus 1 cubed minus 1. And of course on a test you're welcome just to leave it in this form. Let's go ahead and simplify. 4 to the 3/2, so 4 to the 1/2 is 2, and then you cube that and get 8 times 4 over 3 is 32 over 3. 4 cubed is 64, minus 4 is 60. And then plus 1 cubed minus 1, those go away. 1 to the 3/2 is 1, so we get minus 4/3. And when you work this out, we end up with 208 over 3 for our final answer here. But again, the key step is to first find your antiderivative and then plug in your upper and lower limits of integration.